Today's lesson is on 10.1, making predictions on solubility. Point one, making predictions about solubility. So the term soluble, we've talked about this before, and it is just a relative terms because, in essence, the idea of something soluble, you would think, hey, it's something that dissolves readily. It dissolves, completely. But understand that for something to be considered soluble, we don't need very much to be able to dissolve in 100 milliliters of water. All we need is a measly 1 gram of substance to be able to dissolve within 100 milliliters of water. Understand that some things can dissolve more than just 1 gram, but all we need is a little bit, just 1 gram. For something to be considered slightly or partly soluble, all you need is anywhere from 1 gram to 0.1 gram to be able to dissolve in at least 100 milliliters of solvent. And for something to be considered insoluble, all you need is at least 0.1 gram of it and less to dissolve in some kind of a solvent. So the effects of ion charge on solubility. Compounds of ions with small charges tend to be soluble. Okay, so ions with a large charge tend to be insoluble. Okay, so when we're talking about small charges versus large charges, we're talking about small charges having a +1 oxidation number or even a -1 oxidation number. Large charges really can be anywhere from a +2 oxidation to a +3, +4, right? So that's what we are talking about by when we refer to small and large charges in terms of ions. That's why typically phosphates are insoluble. For those who remember phosphate, PO4 -3. Look at that, large charge. Alkali metals, and here's a hint to help you with the solubility table that I'm going to share with you in a few moments. Alkali metals are typically soluble in water because they all contain a +1 oxidation number. So the effects of ion size on solubility: when an atom gives up or gains an electron, the size of the ion that results is different from the size of the original atom. So understand that, believe it or not, when a halogen gains an electron on that shell to fill its octet, understand that the radius of those anions slightly get larger. Okay, we'll see. I think I have a diagram later on in here that will kind of share that. While these alkali metals, in fact, remember that their radius is very large with that 1 valence electron, right? That it's barely holding on. Remember, if you remember that class just before we left for the March break and before we went into self-isolation, that 1 lonely electron on that valence shell is barely holding on. And so once that gets lost or given up to, let's say, one of the halogens, its radius will in fact get smaller. Okay, so small ions bond more closely than large ions, right? Because small ions have a closer connection with that nucleus. Bonds between smaller ions is stronger than the bonds of larger ions with the same charge. Okay, so if you've got a smaller ion in terms of radius size between a larger ion, even though they are both +1 charges, they will not have the same type of bond that the smaller ions there. So therefore, compounds with small ions tend to be less soluble than compounds with large ions, because those large ions will, let's say, hold on with the bond a lot greater. Okay, so think about this question. Explain why the radius of a cation gets smaller while the anion gets larger in comparison to their neutral atom. Well, as we mentioned moments ago, right, if you look at this diagram here, here's lithium. So notice the radius is larger, but once it loses that electron, that radius becomes smaller because it's lost the one electron that is being repelled by all the inner electrons. The same thing goes with any, notice how any of the cat ions, right? They will actually, the cations, when the cations form, they all become smaller than their neutral atom. Anions, on the other hand, okay, let's use a different color here. Anions, on the other hand, the anion will in fact get larger because, remember, this nucleus has the ability to attract all of those electrons. Right? It's got the same number of protons as it does electrons, so it's able to bring that valence shell closer together. The minute you add an extra electron to that valence shell, remember that nucleus has the ability to attract X number of electrons. When you add an additional electron, all of a sudden now the inner electrons will repel those outer ones by a little bit. Hence the reason why the radius gets larger for anions with respect to their neutral atom. Okay, so when fluorine gains its electron, its radius becomes smaller. When when lithium, on the other hand, loses its electron, it in fact gets smaller. Okay, I think I said that correctly. Okay, so when fluorine gains it, it becomes larger. When lithium loses it, let's say to a fluorine, it will get smaller. Okay, so I'm going to share with you this solubility guideline. So here's the solubility guideline. You're going to see a version of this. There's one in the appendix on Google Classroom. You'll also see it as a link in the YouTube video. But it's also on the back of the periodic table that I gave you. Okay, so on the back of the periodic table I gave you, you will find the solubility guidelines. There's some more to the solubility guidelines. So if you don't see a cation or anion on the solubility guideline, look at the bottom to see some of the others that we've not managed to fit into these guidelines. But anyhow, this is what we are going to use to help predict the solubility. It's not enough to just go and say, well, does it have a small charge? Does it have a large charge? Because not always is that the case. So if you look at here, right, we've got the small charges, right? We've got chlorine, bromine, and iodine. They're considered soluble, but it all depends on what these are going to bond with, which will determine whether they're soluble or not. So it all depends on what's going to bond with any one of those three, because if one of these three bonds with one of these three are considered insoluble, and based on these guidelines, whatever is up at the top, that takes precedence over everything. Okay, everything below that, it all depends on where they are on this scale. Okay, and that's what's going to take precedence in terms of solubility, and that's what we're going to look at in 10.2 right now. Okay, so we're going to move over to 10.2. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.